Lesson 1 here is the first of 25 Introduction plus Review lessons, and these lessons are titled according to one of the 10 major topics covered in Shormann math. And the first topic up is number, and so you'll see this up at the top right here. It says Lesson 1, number. So there's 9 other major topics, and that's how these first 25 lessons will be titled. And something about numbers are abstract ideas, and that means the same numeral. Numerals are the symbols we use to describe numbers, like this number 5 on the U.S. Navy Blue Angel aircraft. The same numeral that can be used to describe an infinite number of situations. Now, before we talk about number anymore, let's look at this topic of what is mathematics. And if you haven't done Shormann math before, then this is maybe something you haven't considered really is, well, what is math? Why am I doing it anyways? What's it about? And before we talk about that, let's just think about a few things here. Look over here on the left. I always put the 4 topics, or however many topics there are in a lesson. They'll be listed over to the left, just to give you an idea of what the lesson's about. Hopefully you've also done your reading assignment and briefly read over the reading assignment for this lesson, spending 5 to 10 minutes on that, just getting familiar with things, not reading every single word, but just getting familiar with what's going on. And you're supposed to be actively participating, taking notes on this lecture. So there's some things that you don't need to write down. There's some things you do need to write down. And something you always write down are the example problems. And you're doing mathematics when you do the example problems. That's the best way to learn math, is by doing it. So always write down the example problems. Work the problems with me. Pause and rewind as you need to. Then, like on the screen right now, you see a lot of words. You don't need to write all of that down. Listen. If there's something in particular that is of special interest to you, a Bible verse, a quote, an idea, then feel free to write those things down. Be creative. Make the notes your own record of this course. So just getting started here, the fact that you are taking a Precalculus course, that means you are smart. And in fact, by the time you're finished with Shormann Precalculus, you probably will learn more math than most people in the world will ever learn. And I think that's something you should be proud of, for sure. But even more, I think you should consider the words in Proverbs 15:33, and that was at the beginning of the reading assignment. The fear of the Lord is instruction in wisdom, and humility comes before honor, especially that part. Humility comes before honor. So that verse is not saying that God wants you trembling like a coward in fear of him when it talks about the fear of the Lord. If that's what you think it means, then you don't know much about him. But not to worry. You'll know him well after you complete this course, because we'll talk about God a lot. And it's okay to be proud of your accomplishments. So it's not what this is saying either, is not to be proud of your accomplishments. But as Proverbs 15:33 proclaims, it's better for you to be humble, thankful, grateful, kind, using your knowledge to serve others, than to seek honor, pride, self-centered, using your knowledge like a power-hungry weirdo to gain an advantage. So yes, we just used the word weirdo in our math course, so just don't be a weirdo as you think about and do your math and learn new things. So on to this topic, what is mathematics? Mathematics is actually many things wrapped into one. It's not easy to have just one definition about it. So here's a few that famous mathematicians and math teachers have come up with over the years, and you don't need to write these down. The science which investigates the means of measuring quantity, that's by Leonard Euler. The foundation of exact thought as applied to natural phenomenon, that's by Alfred North Whitehead. Mathematics is a classification and study of all possible patterns. W. Sawyer, a math educator. And a study of space and quantity. Morris Klein, another math educator. So notice what we've already done. We've studied history. We started out studying history in here, and I think that's important because it helps give you an idea and get you connected with people who have thought deeply about mathematics. And how are we supposed to understand what it is if we just kind of think of it on our own? I mean, maybe you could, but it helps to see what other really smart people, really thoughtful people have said about it as well. So Alfred North Whitehead, he said that mathematics is abstract, and that means it deals with properties and ideas of things just because they are things, regardless of feelings, emotions, sensations we might connect with them. So just Thinking about the U.S. Navy Blue Angel plane number 5, there was one Blue Angel in that photo, and there's one and no other value works. It doesn't matter how I feel about this picture. There's one Blue Angel there. I can't say that there's 6 U.S. Navy Blue Angels in this photo. Math helps us know if we search for truth, we can often find it. And because math reveals truth to us, it naturally leads to the question, is there a source of truth? In other words, mathematics points us to God. Only the fool says in their heart there is no God, and that's in Psalm 14:1. And if you have foolish thoughts like that and have not yet accepted God's saving gift of faith, like it's described in Ephesians 2:8 and 9 and elsewhere, then I want to encourage you right now to consider doing that. Believe and repent, and be baptized in the name of God's Son, Jesus Christ, who gave his own life for the remission of sins. You'll receive the gift of the Holy Spirit. So I can tell you those things. I think it's important that I do that, but God has to change your heart. So if you aren't a Christian, if you don't want to be a Christian, then I just ask that you respect my beliefs about that, and hopefully that will be fine with you. And when we trust Christ as our Savior, though, I believe that we can know more things, but not everything, about our origins, about what we are supposed to be doing right now, and about what will happen in the future. That's what Proverbs 1:7 says. We can see the unity and diversity, a topic we'll discuss a lot in this course. We can see that found in the Holy Trinity, where Scripture proclaims God is Father, Son, and Holy Spirit. 3, but also 1. We should not be surprised that God's attributes, like his divine nature and eternal power, are revealed in mathematics. So, we can't see his divine nature. Romans 1:20 says his invisible attributes, like those, are clearly seen in creation. So we have no excuse for denying God's existence. So we can see the effects of his power, like a volcano erupting, or a massive wave breaking, or an eagle grabbing a salmon out of the water with its talons. We don't see where all that power comes from, though. So sometimes we use the word Godhead. That's also used to describe God's divine triune nature, and that in turn reflects his perfect example of unity and diversity. So just talking about unity and diversity and its connection to mathematics, God has made it obvious that unity and diversity exist. Being able to describe it, that can lead to confusion, but don't feel ignorant if you don't fully understand how one thing can also be many. How can God be Father, Son, and Spirit? Well, there's lots of other examples of that too. In fact, even though it's true, nobody completely understands unity and diversity. So you're in the crowd of everybody else in the world if you don't totally understand it. But we can learn a lot about it, though. He's revealed his attributes to us, just not yet fully. That's what 1 Corinthians 13:12 says. So sometimes you may hear when you're learning that you have to have mastery over something. But what about this? What about understanding some things, but not everything about a concept? That's what's going to happen in Precalculus. And when you're really thinking about learning long term, that's what it's going to be like. When you're going to learn as a lifelong pursuit. When you learn something about a concept and some things, but not everything, that requires humility. It requires patience, joy, perseverance, and prayer. Whether you're a Christian or not, I want to make it clear that attitudes of pride, arrogance, impatience, general grouchiness, weirdo-ness, that won't make learning math any easier. So to help you get a better understanding of things that relate to the concept of unity and diversity, you can study this table. You don't need to write this down, but you may have some questions in the practice sets later about it, so you know where to find it. It's in the Lesson 1 reading assignment. But God is also 3 persons, Father, Son, Spirit. Jesus Christ is also fully divine, fully human. You see the connection there between one thing and many things? Something general can also be particular. We can have particular examples of a general thing. That's algebra. Something abstract can have concrete examples of it. Numbers are abstract, right? But we can have concrete, specific examples, like the number 5 on the U.S. Navy Blue Angel aircraft. Some others that are especially important in math: infinite and finite, continuous and discrete. Now, if there's a couple of things to write down here, one is this, that mathematics is considered the language of science, and it's a tool for studying God's creation. So there's a big connection between math studies and science studies, like your chemistry class, your biology class, your physics class. Since God has an abstract nature, it makes sense that he would design our brains with the ability to use an abstract tool like mathematics to help us learn about how his creation operates. And think about this: humans and no other organisms were created in God's image. That's what Genesis 1:26 says. He designed us to be creative just like him. And as the famous scientist Johannes Kepler said, when we study God's creation, we are thinking God's thoughts after him. And that gives us and no other organism the ability to manage his creation. So that's what Genesis 1:28 tells us, is to rule over his creation, meaning be a good manager of it. So let's finish this introduction with another definition. This is the one that we're going to use the rest of this course, and this would be another thing to write down. Mathematics is the language of science and a God-given tool for measuring and classifying pattern and shape. So you can see some of the themes that are in those other 4 definitions that we discussed earlier in this definition here, but that's what we'll use. Mathematics is a language of science and a God-given tool for measuring and classifying pattern and shape. Let's move on to part B on a brief history of number, and we're still not doing much with number. We're just studying the history of it now, but hopefully you've seen some things, and maybe you're starting to think of mathematics in a different way, that it's not what you thought it was all these years. The famous math educator John Saxon, he said a number is an idea, and that's a good way to think about it. It's an abstract idea that applies in an infinite number of situations, which we mentioned earlier as well. We use numerals as symbols representing the idea of numbers. Numbers, like math itself, they're abstract rules. So think about that Blue Angel aircraft again. The oneness of that Blue Angel aircraft in that photo, that's an idea that can be applied to a variety of situations. One blue angel, one slice of toast, one joyful thought, and on and on and on. It seems strange that one thing, a number, can describe many things. It's strange, but it works, right? I mean, there's nothing there that says it doesn't. The abstract nature of our Creator, one God, 3 persons, that reminds us we should not be surprised to find aspects of his creation that have abstract qualities too. So briefly going through the history of number here, the Egyptians and Babylonians, 2500 BC to AD 260, around in that time frame. Not much is known of the pre-flood world before the Babylonians, and that kind of makes sense since everything got wiped away. After the flood, though, Babylon grew, later to be dispersed by God, and the oldest known mathematical documents are from the Babylonians. And one reason mathematics stagnated for them, it's interesting, it has to do with what they worship. They worship the creature, not the Creator. But why would that matter, what they were worshiping? Well, mainly because creatures are not God, right? They don't write instruction manuals like a Bible. Hopefully it's not a surprise to you that if you worship a creature like a duck, that duck isn't going to say, "Hey, just ask me. I'll teach you great and unsearchable things you did not know." No, creatures don't say things like that. God does. That's actually Jeremiah 33:3. That's why history reveals that learning stagnates when people worship creatures, but it flourishes when individuals, cities, and nations follow Christ. It's true. Study history. You'll see that. Moving on to the Pythagoreans, maybe you've heard of the Pythagorean theorem. Pythagoras, he's credited with developing that, and we'll cover that in Lesson 8 and lots of other places because it's a really useful formula. Although the Babylonians, supposedly they also knew about that. And Pythagoras, he had a religious following of people who worshiped the reflection of God, mathematical order. They saw the mathematical order in creation, but they didn't worship God. They worshiped that order. They worshiped numbers, actually. That's kind of weird that they worship numbers. Now we had the Greeks. Mathematics flourished with them for 600 BC to AD 450 about, and they did a lot of great work on human reasoning. We're going to talk about some of that later, but they went too far in idolizing human reasoning. So things that didn't make sense, like infinity, how could a number just be increasing forever? Like irrational numbers like the square root of 2 and pi, things like that, they basically ignored those. And this is why they shied away from arithmetic and from algebra. They focused more on geometry, where they didn't have to mess with numbers. And their pursuit of geometry helped to develop our understanding of mathematics' abstract nature. But since they couldn't get away from just using a compass and a straight edge, a drawing compass to make circles and arcs and a straight edge to make lines, mathematics stagnated with them for that and other reasons. Now, in the time frame 1030 BC to AD 1700, Chinese, Inca, Mayan, American Indian, supposedly, these were all isolated from the mainstream of mathematical development, but they nevertheless had their own decimal numeral systems, all of which display vestiges of Babylonian ancestry, such as a widespread use of the base 60 or sexagesimal system is what the base 60 system's called. And we use that today still. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle, things like that. And the Hindus and Arabians, 200 BC to AD 1200, the Hindu-Arabic numeral system, that's named after the Hindus who probably invented it and the Arabs who passed the system on to Western Europe. They also invented negative numbers and the numeral 0 around the time of Christ's birth. About the same time the Mayans from South America did. Here's an example of the Mayan numeral system where you can see that numeral 0 right there. I mean, think about that. 0 is nothing. 1 is something. How do you go from nothing to something? That's kind of a deep thought. And people all over the world at the time of Christ's birth were thinking about that. Perhaps these civilizations were less isolated than some people think. Mathematics, it's the language of science, and getting more into how we use number, we have symbols that mean something. That's what a language does, right? It has symbols that mean something. So our most common modern arithmetic symbols are plus for addition, minus for subtraction, the times or dot or parentheses, we use all of those for multiplication, and a division symbol. Most of those were first used in the 15th to 17th century, so not that long ago when you look at the history of mathematics. The post-flood recorded history, that is. We also use plus and minus to describe positive and negative numbers also, like a +3 and a -3. So it's important to know that math is considered the language of science. We've mentioned that already. So like every other language, it has its own symbols. So during Shormann Precalculus, we're going to learn many new symbols, a lot of them. And you'll also see that using the symbols is faster than writing out the words or phrases corresponding to each symbol. So yes, you'll have new symbols, and sometimes that's kind of a pain to have to memorize all of those new symbols, but you're learning a language as you do mathematics, and to become fluent with it, you have to repeat the use of it. Now let's move on to part C and start doing some examples. Number sets and set notation. So refer to the lesson 1 rules and definitions for the different types or sets of numbers, like real numbers, rational numbers, etc., and the set notation symbol. So be prepared to answer questions like the ones that follow here. And all of this is review, meaning review from Shormann Algebra 2. So use the lesson references for Shormann Algebra 2 that are on the e-learning campus as you need to if this is totally new to you. So example 1, true or false, all counting numbers are also integers. Well, that's true. And so you might want to have your reading assignment open so you can refer to those rules and definitions as you go through this. So all whole numbers are integers. All whole numbers include counting numbers. So counting numbers are integers too. Moving on to example 1.2, use a sentence to describe the set notation in each of the following, and which one best represents the set of counting numbers. So thinking about 2 different questions here. So first let's write a sentence for all 3 of these. And so in A, think about what that says there. X is a member of, that's what that E looking symbol means is a member of, and then the R, the funny looking R there, is the set of real numbers. So x is a member of the set of real numbers. The vertical line means such that, and then x is greater than equal to 0. X is a member of the set of real numbers such that x is greater than equal to 0. So we'd write that like this. X is a member of the set of real numbers such that x is greater than or equal to 0. So write that out. You need to write that down for that. Remember, we're doing these examples. This is where you write things. Let's move on to B. Y is a member of the set of Q. Q stands for rational numbers. Y is a member of the set of rational numbers such that y is not greater than. That's what this means, not greater than. Well, if it's not greater than, there's three things something could be. It could be equal, it could be greater, it could be less. So if it's not greater, it's got to be the other two. It's got to be less than or equal to. So we say y is a member of the set of rational numbers such that y is less than or equal to 2. And then for set C, Z is a member of the set of Z. Well, that's an integer. That symbol represents integers. Z is a member of the set of integers such that Z is greater than 0. Well, if it's integers, that means like non-decimal things, like a 0, a 1, a 2. So if it's greater than 0, that means it has to start with 1, and then 2, and then 3, and so on. So C, that represents the set of counting numbers. So that would be our second question there. Which one best represents the set of counting numbers? That would be the set represented in C. So that represents the counting numbers. Look at example 1.3. Use set builder notation to describe the following. So we're kind of doing the opposite of what we did in example 1.2. Here we'll create the symbolic notation. So A, if set A represents the set of whole numbers, use set builder notation to describe how set A is a subset of the integers. So what we could do there is just use our brackets there for representing a set. We can say set A is a subset. That's this symbol right here. Is a subset. That's what that means. Is a subset of Z. And so we'll kind of make our Z, and however you want to do this, but I'll kind of just do like a little double line there in the middle to represent the set of integers. A is a subset of the integers. And then B, X is a member of the set of rational numbers such that X does not equal 1.618. So let's just start with our set brackets there, and X is a member of the set of rational numbers. That's the Q, and so we'll put these little lines on there to kind of use that font that they use for that. X is a member of the set of rational numbers such that, that's our vertical line, X, if we say X equals, we just put an equal sign, right? If it does not equal, we put a slash through it. X does not equal 1.618. So that would be the notation for that. And then C, X is a member of the set of natural numbers such that X equals -2. Counting numbers and natural numbers, those are the same thing. So they begin with 1. Therefore, this is an empty set, since -2 is not a natural number. So we can write the symbolic notation and write the set out. We can say X is a member of the set of natural numbers such that X equals -2. And then we'll say that that equals the symbol that we use for empty set. It's like a 0 with a slash through it. That's an empty set. There's nothing in there. So if you wrote that answer out just like that and didn't say it was an empty set, then that's wrong. So you have to have that that's an empty set. Example 1.4, which of the following is a real number? So you can see there we have a 6, a 3.5, and a -11. So real numbers include integers, they include decimal numbers. So actually all three of those are real numbers. So the correct choice would be choice E. Look at example 1.5 on intersection and union of sets. So you've been given two sets there, set A and its numbers, set B and its numbers are elements. Elements is the word to describe the members in a set. So A, find A union B. And then B, find the intersection of A and B. And then C, use a Venn diagram to represent sets A and B. So if you look at your rules and definitions, you'll know that the union of A and B, that includes all non-repeated elements, or numbers in this case. They're all numbers, so all non-repeated numbers. And so let's just start writing that out. We can say A union B is equal to -5, -4. Now, they both have a -5. They both have a -4. So we don't say -5, -5. We just use it once, non-repeated. A -3. And I'm just trying to do these in order here. And then +3 would be next. Then a 6 in B. An 8 in both of them. A 10 in B. And 11 in A. And so there's the union. B, the intersection. A, this symbol means intersection. A intersection B. That's all of those elements that are repeated, so that they both have. So they both have a -5. They both have a -4. They both have an 8. And so there's the intersection. That's where they intersect. That's where they're equal. And then C, we want to use a Venn diagram to represent sets A and B. Those are named after John Venn, and like Leonhard Euler, who is considered one of the most famous mathematicians ever, his father and Euler's father, they were both pastors. John was a pastor for many years himself. The diagrams that Venn was named after, they were developed from Euler's work on logic and Euler circles, sometimes they're called, and we'll talk about those later. Now, apparently Euler developed some of his ideas on the subject from Leibniz, who's the co-founder of calculus, his writings on the subject. So all of these men who are influenced greatly by Christianity or were strong Christians themselves, like Leibniz and Euler, came up with some good ways to represent numbers. So here's how we could describe this using a Venn diagram. So here's set A. Call that A. And a lot of times a box is put around the whole thing as well. And so here's set A. And so we have a 3, we have an 11, and I'm going to put the -5, the -4, and the 8 over here, all of those intersecting values. And then I'm going to put set B kind of wrapping around that, like that. And we'll say B is over here. And then those numbers that are in but that aren't part of the intersection, I'll put those out here, like that. So do you see that, how we put the intersecting numbers, those are inside right there where those two circles overlap. So that's how you use a Venn diagram to describe the similarities and differences between two or more sets. In example 1.6, the circles, they represent the members of sets A, B, and C. So use set notation to describe the shaded region or the logic described in each of the following. So starting with A there, we see a set A, a set B, a set C. Hopefully you can see there that the intersection of A and B is represented. Even though there's a set C there as well, that's the main thing that's represented there, is the intersection of A and B. And then in B, we have set A shaded, nothing in set C, so no union or intersection is represented there. So we'd say that these are disjoint, so we could just write that. There's actually nothing represented. They're separate sets, disjoint sets is how we describe that. And then C, we see how B and C are shaded there. So everything in B, everything in C is shaded, so that represents the union of B and C. Last, let's review some special number types and exponents, and let's look at in particular the base 10 and the base 2 systems. And the base of a system relates to its place value. So for example, the base 10 system works in multiples of 10. We also call that the decimal numeral system. So starting over here on the right, we could think of 10 to the minus 2. That'd be 1 over 100, right? It's 1 over 10 squared. And then 10 to the minus 1. And then there'd be a decimal place right here, because 10 to the minus 1 is 1 over 10. It's the tenths place, right? And then we have the 10 to the 0. 10 to the 0 is 1, right? That's the ones place. So if you're thinking about place value and your different places, you'd have 10 to the 0. Then the tens place is 10 to the 1. The hundreds place is 10 squared, or 10 times 10. The thousands place would be next, 10 cubed, and so on. Use of the base 10 system dates back to at least 3000 BC. Now the base 2 system, that's important in computer applications where the entire system is run by switching electric current on or off at different times and locations. We have a topic called computer math. That's lessons 24 and 25. So computers are an important part of mathematics, and mathematics is important in computers. So this base 2 system, it's got a similar pattern to the base 10 system, but you just have two values in it, 0 or 1. And so you could have a 2 to the third place. You could have a 2 squared place. You could have a 2 to the 1 place, and a 2 to the 0 place, and a decimal point even, and a 2 to the minus 1 place, and a 2 to the minus 2, and so on and so on. Can we convert between base 2 and base 10? Well, we must be able to, because if a computer is run off the base 2 system, and I mean, you're looking at a computer screen right now, there's not just a bunch of ones and zeros. Those aren't the only digits that you see on there. You see base 10 digits all over. So there must be some way to convert. Let's do that right now. Look at example 1.7a. Convert that binary number to base 10. So remember, in binary, 1 means it's on. That means we use it. 0 means it's off. It means we don't use it. So think about this. Just look at our place value chart that we drew up there. And so 2 squared, 2 to the 1, 2 to the 0, and 2 to the minus 1, those would all be on. And so what does 2 squared equal in base 10? Well, that's equal to 4, right? 2 squared. 2 to the 1, that equals 2. 2 to the 0, that equals 1. What about 2 to the minus 1, or 1 over 2? That's 0.5, right? So what do we have there? We have, for A, we have a 4 plus a 2 plus a 1 plus a 0.5. That's equal to 7.5. That's what 111.1 equals in base 10. Let's do another example, and let's erase these. Look at the next one, 1, 0, 0, 0, 1. So we have 2 places that are on and 3 that are off, and there's no decimal there, so that means we'd start with 2 to the 0. So 2 to the 0 is just 1. And then we have 3 that are off. So this would be a 0, this would be a 0, this would be a 0. We need a 2 to the 4th in there too, because 2 to the 4th is on. So what is 2 to the 4th? Well, that's 16, right? So for B, 1, 0, 0, 0, 1 in base 10, that's 16 plus 0 plus 0 plus 0 plus a 1 is 17. That's the base 10 equivalent. Computers run on electricity. They're either on 1 or off 0. How do you get some kind of computer hardware and software to work together to create a 17? Well, you convert between binary and base 10. Almost done with lesson 1 here. A couple more examples. Example 1.8, moving on now to some other types of numbers. Simplify the following and assume I equals the square root of -1. So we're looking at complex numbers here, where I, that symbol, means the square root of -1. So that also means that I squared equals -1. And so we simplify by breaking things into groups of I squared, because that equals -1. That's one way we simplify these. So in A, let's do that one first. -2 plus a 4 factorial is what that means. So hopefully you know 4 factorial, that'd be 4 times 3 times 2 times 1, and that would be a 24. And then a negative 6 and a negative 11. So minus 2 and 24, that's 22. Minus 6 and minus 11, that's a minus 17. Add those together and you get 5. So just reviewing here some basic numeral arithmetic and special symbols to keep in mind. In B, we have the square root symbol there. 4 times the square root of 2 times the square root of 243. Now, these problems, this might be something to make a note of, is that they're normally designed so that when you see a big square root value like the square root of 243, try to break that up. Simplify it by factoring out a perfect square from it. So you can get your calculator out to do this, even though I don't want the answer in a calculator mode. But what are some things like perfect squares, like a 25, a 36, a 49, things like that? 243 divided by 25, that doesn't give you like two simple factors, but 81 does. If you did 243 divided by 81, you get 81 times 3. So that simplifies to the square root of 81 times the square root of 3. And why do we look for perfect squares that are factors? Well, because those, the radical sign simplifies, right? Square root of 81 is just 9. So we can say that that number is 9 times the square root of 3. So now, this problem, we can say it's 4 times the square root of 2 parentheses 9 square root of 3 plus just a square root of 3. That means 1 times the square root of 3, right? We have 1 square root of 3 value there. So 9 square root of 3 plus 1 square root of 3 would be 10 square root of 3, right? So now we have 4 square root of 2, parentheses 10 square root of 3. Multiply the non-radicals of 4 and the 10, that's 40. Multiply the square root of 2 times square root of 3, that's square root 6. And we'll just leave the answer like that. You're not supposed to write these in a decimal form. That's not the goal here. So when you see something from lesson 1 like that, know that you're not supposed to write the answer as a decimal form. And then in C, simplifying that, 7i. Now I cubed, let's just do that over to the side. That equals I squared times I, right? And I squared equals negative 1, so this can simplify to negative I. So we have a minus I minus 3 plus 2i. So simplify inside parentheses first. So we can add this minus I plus 2i. That's like we have a negative 1i and a plus 2i. That'd just be I. So that simplifies to 7i parentheses minus 3 plus I. Now expand. 7i times minus 3, that's a minus 21i. 7i times I, that is 7i squared. But I squared equals negative 1, right? So normally when we have real parts and complex parts, we write the real part first. So 7 times I squared is 7 times negative 1, that's negative 7. Minus 21i. That would be the standard acceptable way. It's not wrong if we said minus 21i minus 7. It's just not the standard form. We want to write these in the standard form. Problem 9, a fundamental algebra 1 level concept. It's also a concept every student gets confused about. So that's why we're doing it again. So when you see minus 5 squared like in A, that means the opposite of 5 squared. So you do the 5 squared first. That's 25. So the answer is the opposite of 25. Don't do minus 5 times minus 5. That's problem C, where you have parentheses around it. That's minus 5 times minus 5. But B, that's the opposite of 1 over 5 squared, right? 5 to the minus 2 is 1 over 5 squared. So that's minus 1 over 25. C, like we said, that's minus 5 times minus 5. That equals positive 25. Make sure that you see the difference there and that you hopefully still aren't confused from Algebra 1 on those type of problems. And D, 1 over minus 5 times minus 5. That'd be a positive 1 over 25. Example 10, it doesn't say solve, it just says simplify to eliminate all unnecessary exponents. So in A, do you see the 3 cubed over 3 cubed? So, and we can write that as 3 cubed times 1, right? So factors are things that we can cancel. We can always write anything as have a 1 as a factor of it, right? So that cancels. Now we have 5 squared times 3 to the 4th over 1. So A is just equal to 5 squared times 3 to the 4th. That's how we'll leave the answer for that one. In B, we don't see anything readily that we can cancel, so expand first. So we'll have 2 cubed, 6 to the minus 3 over 6 squared times 4. And I'll put a time symbol right there too. And then minus, we put a minus there because there's a minus right there. And again, 2 cubed on the top times that 6 to the 5th over 6 squared times 2 cubed. Now hopefully you see right away this 2 cubed, that 2 cubed will cancel. And then 4, that's equal to 2 squared, right? So we could think about it like that. And in the first expression there, we'd have a 2 cubed over 2 squared. That's like a 2 to the 3 minus 2 in the numerator. So 3 minus 2 is 1 or just 2. And then move the 6 squared up to make it a 6 to the minus 2. So we'd have minus 2 minus 3 is 6 to the minus 5. Minus, and then move that 6 to the 5th, move the 6 squared up to make it a 6 to the minus 2 again. 5 minus 2 is 3. So 6 cubed. And so that's how we'll leave that. We don't have to calculate a number on that. And that is all for lesson 1.